The year is 1943, and somewhere in occupied France, a Luftwaffe recovery team surrounds the wreckage of an American fighter. The aircraft is massive, far larger than anything they've seen from the Allies. Its nose is crumpled, one wing torn away, but the heart of the machine remains intact, a radial engine of extraordinary proportions. As German engineers approach, they don't yet realize they're staring at the beginning of their obsolescence. This is the Republic P-47 Thunderbolt, and hidden within its cowling is a 2,000 horsepower Pratt & Whitney R2800 double Wasp engine. When German technical intelligence officers first laid eyes on this American creation, they faced a devastating truth. The technological gap had become unbridgeable. This is the story of that realization, of engineering hubris meeting industrial reality, and how one captured aircraft revealed the future of aerial warfare. The giant among fighters. When the P-47 Thunderbolt first entered service in late 1942, even American pilots weren't sure what to make of it. Weighing nearly 7 tons when fully loaded, it was the heaviest single-engine fighter of its time. Pilots nicknamed it the Jug because of its rotund fuselage, and some questioned whether this enormous machine could truly compete with the nimble Messerschmitt Bf-109s and Focke-Wulf FW-190s they would face over Europe. The skepticism was understandable. The P-47 dwarfed other fighters. Its fuselage was wide enough to accommodate a supercharger system that required ducting running throughout the aircraft's belly and back to the tail. The cockpit sat so high that pilots needed a small stepladder to climb aboard. Everything about it seemed excessive, almost comically oversized. German intelligence officers, reading early reports, initially dismissed it as another example of American industrial excess without tactical sense. But beneath that bulky exterior lay something revolutionary. The R2800 double Wasp engine represented the pinnacle of American radial engine development. 18 cylinders arranged in 2 rows, each one precisely machined and balanced. At maximum power, this engine could generate 2,000 horsepower, later versions pushing beyond 2,500 horsepower with water injection. This wasn't just an incremental improvement over existing designs. This was a quantum leap in aviation power plant engineering. The engine's architecture told a story of different engineering philosophies. While German designers had pursued inline, liquid-cooled engines like the Daimler-Benz DB601 and DB605, seeking elegance and aerodynamic efficiency, American engineers had doubled down on the air-cooled radial. The R2800 was brutish, heavy, and seemingly outdated in concept, yet it delivered unprecedented reliability and power. It could absorb tremendous battle damage and keep running. Cylinders could be shot away, and the engine would continue turning. This robustness would prove decisive in ways German engineers never anticipated. The capture spring 1943. An American P-47 from the 56th Fighter Group gets separated from its formation during a bomber escort mission over France. The pilot, low on fuel after extended combat, realizes he won't make it back across the channel. He spots a field, brings the Thunderbolt down gear up in a controlled crash landing, and manages to escape before German forces arrive. Within hours, Luftwaffe technical intelligence has secured the site. The recovery operation is meticulous. Unlike earlier captured Allied aircraft, this one commands immediate attention from the highest levels of German technical command. Orders come directly from the Reichsluftfahrtministerium, the Reich Aviation Ministry. They want this aircraft intact, and they want it analyzed immediately. The P-47 is carefully loaded onto a transport and moved to the Luftwaffe testing facility at Rechlin, northeast of Berlin. At Rechlin, a team of Germany's finest aeronautical engineers gathers. These are men who have designed some of the war's most advanced aircraft. They've worked on the FW-190, arguably the best fighter Germany has produced. They've contributed to jet engine development, to rocket propulsion, to innovations that in some areas still lead the world. They approach the P-47 with professional curiosity, mixed with a certain confident superiority. After all, German engineering is the envy of the world. What could the Americans possibly teach them? The initial inspection reveals the aircraft's unusual construction. The fuselage is all-metal monocoque, similar to German designs, but heavier gauge. The wings are thick, designed for structural strength rather than aerodynamic refinement. The cockpit is spacious, with more instrumentation than they expect. But it's when they begin examining the engine that the atmosphere changes. Removing the cowling reveals the R2800 in its full complexity. Even before detailed measurements, the engineers can see this is something different. The size alone is staggering. The engine weighs 2,360 pounds dry, comparable to many complete small aircraft. But it's not just size that impresses. It's the precision of manufacture, the quality of materials, the sophistication of the supercharging system. The engineering analysis lead engineer Friedrich Schlemp oversees the teardown. Schlemp is no amateur. He's worked on BMW radial engines, consulted on the development of the BMW 801 that powers the FW190. He understands radial engine design intimately. As his team begins disassembling the R2800, he takes careful notes, his expression growing progressively more serious. The connecting rods are masterpieces of metallurgy. Each one is forged from a nickel-chrome molybdenum steel alloy, heat-treated to precise specifications. The machining tolerances are extraordinarily tight, tighter than current German production standards for similar components. Schlemp picks up one of the master rod assemblies, feels its weight, examines the bearing surfaces. He knows immediately this represents a level of mass production capability Germany doesn't possess. The cylinder barrels tell another story. Each one is night-righted, a surface hardening process that increases wear resistance. The fins are deep and numerous, optimized for air cooling even under extreme combat conditions. When Schlemp examines the valve train, he finds sodium-cooled exhaust valves, an advanced feature Germany has experimented with but not implemented in production. Here, on this American engine, it's standard equipment. But it's the supercharger system that truly astonishes the German team. The P-47 uses a turbo supercharger, a General Electric design that uses exhaust gases to drive a turbine, which in turn compresses intake air. This allows the engine to maintain full power at altitudes where normally aspirated engines would gasp for air. The concept isn't new. German engineers understand turbocharging. What shocks them is the execution. The turbine wheel spins at speeds exceeding 20,000 RPM. The materials must withstand temperatures above 1,500 degrees Fahrenheit. The bearings must function in an environment of extreme heat and mechanical stress. The Germans have built experimental turbocharged engines, but they've struggled with reliability. Turbine wheels disintegrate, bearings seize. The systems require constant maintenance and frequent replacement. Yet here is an American turbo supercharger designed for combat operations, built to run for hundreds of hours between overhauls. Schlemp requisitions specialized testing equipment. Over the following weeks, his team conducts metallurgical analysis of key components. They measure hardness, tensile strength, heat resistance. They examine the fuel injection system, the ignition timing, the propeller governor. Each system reveals the same pattern: sophisticated design backed by manufacturing precision. The fuel system particularly impresses them. The R2800 uses a Stromberg injection carburetor capable of precise fuel metering across a wide range of operating conditions. Water methanol injection provides emergency power boost. The entire system is designed for reliability under combat stress. German fighters have experienced fuel system failures during negative G maneuvers. The P-47 system shows no such weakness. The industrial reality. As the technical analysis progresses, a parallel investigation begins. German intelligence wants to understand not just the engine itself, but how the Americans are producing it. The initial numbers are almost incomprehensible. Pratt & Whitney is manufacturing R2800 engines at a rate exceeding 4,000 units per month by mid-1943. This will increase to over 5,000 per month by 1944. For context, Germany's entire aviation engine production across all manufacturers averages around 4,000 engines monthly. The Americans are producing more of just this one engine model than Germany produces in total, and the R2800 isn't even the only engine Pratt & Whitney manufactures. They're simultaneously producing R1830s for other aircraft, along with several other models. The implications strike the German analysis team like a physical blow. This isn't just an engineering problem. This is an industrial warfare problem of a magnitude they haven't fully appreciated. The quality of the R2800 isn't the result of small-batch artisanal production. This is mass production, at a scale that doesn't compromise on precision or quality. Schlemp's team tries to reverse engineer key components. They machine test parts using German facilities and materials. The results are discouraging. They can produce components that match American specifications, but only in limited quantities, using specialized equipment and highly skilled machinists. The Americans are somehow achieving this precision on production lines, at volume, using semi-skilled labor supplemented by sophisticated tooling and quality control systems. The cylinder barrel, Analysis reveals particularly troubling details. The nitriding process requires specialized equipment and careful process control. Germany has the capability, but limited capacity. Scaling up would require diverting resources from other critical programs. The valve manufacturing presents similar challenges. The sodium filling process, the precise heat treating, the surface finishing all demand capabilities at the edge of German industrial capacity. Then there's the matter of materials. The R2800 uses high-grade aluminum alloys for the crankcase and cylinder heads. These alloys require specific alloying elements, some of which Germany is already short on. The steel alloys for high-stress components demand nickel, chromium, and molybdenum. Germany's access to these materials is limited and becoming more so as the war progresses. The Americans seem to have unlimited supplies. A junior engineer on Schlemp's team does a rough calculation. To produce a German equivalent of the R2800 at meaningful scale would require retooling multiple factories, training thousands of workers, securing material supplies that don't exist, and solving manufacturing problems that would take years to work through. And that's assuming they could match the design performance, which itself is uncertain. The performance gap. While engineers dissect the R2800 in workshops, test pilots take the captured P-47 into the air. Luftwaffe pilot Hans Fey, an experienced test pilot with hundreds of hours in FW-190s and BF-109s, conducts the evaluation flights. His reports add another dimension to the growing concern. At altitude, the P-47 is revelation. At 25,000 feet, where German fighters begin losing power, the Thunderbolt is just reaching its optimal performance envelope. The turbo supercharger maintains manifold pressure, keeping the engine at full power. Fey pushes the aircraft through a series of maneuvers. The roll rate is impressive for such a large aircraft. The dive performance is extraordinary. He pushes the nose down, lets the P-47 accelerate. The airspeed indicator climbs past 500 miles per hour. The aircraft remains stable, controllable. He's never experienced anything like this in a German fighter. German pilots have reported that American P-47's can dive away from any German fighter. Fey now understands why. The structural strength allows dive speeds German aircraft cannot match. The massive engine provides power for zoom climbs after dives. The combination makes the P-47 nearly impossible to catch once it commits to escape. He tests the combat capabilities. 8 50-caliber machine guns, 4 in each wing. The firepower is devastating. He fires test bursts at a ground target. The guns are harmonized to create a cone of fire at combat range. Any aircraft caught in that cone would be shredded. The ammunition capacity is enormous, over 400 rounds per gun. German fighters carry far less, requiring pilots to carefully manage their firing. The combat radius impresses him perhaps most of all. With drop tanks, the P-47 can escort bombers deep into Germany and still have fuel for combat and the return flight. German fighters lack this endurance. They can intercept, fight for a few minutes, and must return to base. The Americans can loiter, waiting for opportunities, maintaining pressure on German formations throughout their missions. Fey's report is technical and professional, but between the lines, the message is clear. This is a superior weapons system, not in every individual metric, but in the combination of firepower, performance at altitude, structural strength, and operational radius. The P-47 can fight on its own terms, exploiting its advantages, minimizing its weaknesses. The strategic implications. By summer 1943, the full analysis is complete. Senior Luftwaffe officers gather at Rechlin for the final briefing. Schlemp presents the technical findings. The R2800 engine represents a capability Germany cannot currently match and likely cannot develop within any time frame relevant to the war's outcome. Even if German engineers could design an equivalent engine, which is uncertain, the industrial capacity to produce it simply doesn't exist. The performance data supports this conclusion. The P-47 operating at altitude has a decisive advantage over current German fighters. The FW-190's performance falls off above 20,000 feet. The BF-109G performs better at altitude, but still cannot match the P-47's power output. German pilots must rely on superior tactics and skill to compensate for the performance deficit. More worrying still are the production numbers. Intelligence estimates indicate America will produce over 15,000 P-47's during the war. This is just one of several American fighter types in mass production. The industrial capacity represented by these numbers dwarfs Germany's entire aviation industry. One officer asks the obvious question: can Germany develop a response? The answer is complicated. German engineers are working on advanced designs. The Focke-Wulf to 152 promises improved high-altitude performance. Jet engines offer revolutionary potential, but these programs are years from operational readiness, if they ever achieve it. Meanwhile, American production accelerates. The meeting concludes with an uncomfortable silence. Everyone in the room understands what the evidence suggests. Germany has lost the industrial technological race, not through lack of engineering skill or innovation, but through sheer scale. America's industrial capacity, combined with technical sophistication that matches or exceeds German capabilities in critical areas, has created an insurmountable advantage. The bomber offensive intensifies. The timing of these realizations coincides with the escalation of the Allied bombing campaign. Throughout 1943, American B-17's and B-24's strike deeper into German territory with increasing frequency. In the beginning, Luftwaffe interceptors savaged the bomber formations. Without fighter escort, the bombers suffered terrible losses. Missions to Schweinfurt and Regensburg in August 1943 see loss rates approaching 20%. Such casualties are unsustainable, but the P-47's gradually extend their range. Drop tanks increase their radius. Improved tactics allow them to escort bombers further into German territory. By early 1944, P-47's are reaching targets deep in Western Germany, and they're not alone. The P-51 Mustang, with even greater range, begins. Arriving in large numbers, German fighter pilots face an impossible dilemma. To attack the bombers, they must penetrate the fighter escort. The P-47's, often flying top cover at high altitude, can dive on German interceptors with tremendous speed and energy advantage. German pilots develop tactics to cope with this, but every tactic has countermeasures, and the Americans have the numerical superiority to adapt. The psychological impact on Luftwaffe pilots is severe. They're skilled, often veterans with hundreds of combat hours, but they're flying aircraft that require perfection in execution to overcome their performance disadvantages. The Americans can afford mistakes. They have more fuel for extended combat. They have more ammunition. They have the engine power to recover from unfavorable positions. They have reinforcements. Luftwaffe pilot Hans-Joachim Marseille, one of Germany's highest-scoring aces before his death in 1942, once said that German fighters were superior because they were flown by superior pilots. By 1944, that equation no longer holds. American pilots are gaining experience, learning from their losses, developing tactics optimized for their aircraft's strengths, and they're flying superior machines. The engineering philosophy divergence. The R-2800 analysis forces German engineers to confront uncomfortable truths about their own design philosophy. German aviation engineering has prized elegance, efficiency, and theoretical optimization. The inline engines powering the Bf 109 and many other German aircraft are streamlined, aerodynamically clean, sophisticated in their engineering. They represent the pursuit of perfection through refinement. The American approach is different. The R-2800 is not elegant. It's brute force made reliable through precision manufacturing and robust design. It's an air-cooled radial, an architecture that inherently creates more drag than an inline engine, but it's also more reliable, easier to maintain, and more damage-resistant. The Americans have accepted aerodynamic compromise in exchange for practical combat advantages. This reflects deeper differences in design philosophy. German engineers optimize for performance metrics. American engineers optimize for operational effectiveness. A German fighter might have superior speed or climb rate under ideal conditions. An American fighter is designed to maintain combat effectiveness after taking damage, after long missions, after being maintained by mechanics with limited training and tools. The turbo supercharger exemplifies this difference. German engineers have pursued mechanical superchargers, driven directly from the engine crankshaft. These are mechanically simpler than turbo superchargers, lighter, and more compact, but they consume engine power to drive them, reducing overall efficiency. The American turbo supercharger is heavier, more complex, and requires sophisticated engineering, but it uses waste exhaust gases effectively, providing free power addition at altitude. German engineers begin to recognize that their pursuit of engineering elegance has sometimes led them away from practical optimization. The best solution on paper isn't always the best solution in combat operations. The Americans have embraced good enough engineering at massive scale, and the results speak for themselves. The material science advantage. One aspect of the R-2800 that particularly troubles German analysts is the material science advantage it reveals. The aluminum alloys, the heat-treated steels, the specialized coatings all point to an American materials industry operating at a higher level than German counterparts in several key areas. Aluminum production is especially revealing. The R2800's crankcase is cast from a high-strength aluminum alloy, designated 142 by American standards. This alloy provides excellent strength-to-weight ratio and good machinability. Germany produces comparable alloys, but not at the volumes required for mass production of large radial engines. Aluminum production requires enormous amounts of electrical power for the smelting process. America has abundant hydroelectric power. Germany does not. The steel alloys present similar challenges. High-performance aviation engines require exotic steels for various components. Crankshafts need alloys with extreme fatigue resistance. Connecting rods need high tensile strength combined with impact resistance. Valve stems need heat resistance. Each specialized application requires specific alloying elements in precise proportions, careful heat treatment, and quality control. Germany's access to critical alloying elements has been a problem since before the war. Nickel, essential for many high-strength steels, comes primarily from sources Germany cannot easily access. Chromium supplies are limited. Molybdenum is scarce. German metallurgists have developed substitute alloys, but these are often inferior to optimal compositions. The R2800 analysis reveals that the Americans face no such constraints. They use optimal alloys throughout the engine. One German metallurgist studying R2800 components writes in his report, "The Americans have solved problems we are still working on, and they've done so at production scale. Their material science is at minimum equal to ours, and in several areas superior. More importantly, they have the industrial base to implement advanced materials in mass production. We have the knowledge, but lack the capacity." The quality control revolution. Perhaps the most important lesson from the R2800 analysis involves manufacturing quality control. German engineers examining the engine find that component tolerances are remarkably consistent. Pistons are virtually identical within microns. Connecting rods are balanced within fractions of a gram. Cylinder barrels show uniform hardness values across production batches. This consistency indicates sophisticated quality control systems. Every component has been measured, verified, and accepted based on statistical process control methods. The Americans have industrialized precision. German production, by contrast, still relies heavily on skilled craftsmen making fine adjustments. A German engine builder might file a connecting rod to perfect balance. An American production line doesn't need to, because the parts arrive within specification. This represents a revolution in manufacturing philosophy. Mass production doesn't have to mean compromised quality. With proper tooling, process control, and inspection systems, mass production can deliver precision that matches or exceeds traditional craftsman methods. And crucially, it can do so at volumes traditional methods cannot approach. German industry attempts to implement similar systems, but the requirements are daunting. Statistical process control requires measurement instruments in large quantities, trained inspectors, and most importantly, manufacturing processes stable, enough to produce consistent results. German factories in 1943 are struggling with material shortages, labor quality issues, and Allied bombing disruption. Implementing advanced quality control under these conditions is nearly impossible. The R2800 becomes a symbol of something German engineers have been reluctant to fully accept. America has not just matched German engineering capability. In crucial areas, America has surpassed it. The gap isn't in theoretical knowledge or design innovation. It's in practical implementation at industrial scale. The jet engine race. As the implications of the R2800 analysis sink in, some German engineers point to jet propulsion as Germany's technological trump card. The Messerschmitt Me 262, powered by Jumo 004 turbojet engines, promises performance that no piston engine fighter can match. Here, at least, Germany maintains a clear lead. The Me 262 is indeed revolutionary. In level flight, it's 100 miles per hour faster than any Allied fighter. Its armament of 430mm cannon can destroy a bomber with a brief burst. If deployed in sufficient numbers with proper tactics, it could theoretically devastate Allied bomber formations. German propaganda seizes on the Me 262 as evidence of continued German technological superiority. But informed engineers and officers know the reality is more complicated. The Me-262 program has suffered from developmental problems, material shortages, and Hitler's interference demanding it be modified as a bomber. Even when these issues are resolved, production numbers remain far below what's needed. The Jumo 004 engines require exotic materials Germany struggles to source. Engine service life is measured in tens of hours rather than hundreds. Pilot training is inadequate. Operational deployment reveals unexpected vulnerabilities. More fundamentally, the jet engine advantage is temporary. Intelligence reports indicate the Allies are developing their own jet fighters. The British Gloster Meteor is already in testing. American programs are underway. German engineers understand that within a year or two, the jet engine advantage will evaporate. And when it does, the Allies will build jet fighters in quantities Germany cannot match, just as they've done with piston engine aircraft. The lesson of the R-2800 applies equally to jet engines. Technological innovation matters less than industrial capacity to implement innovation at scale. Germany can build superior prototypes and limited production. Aircraft. America can build adequate designs in overwhelming numbers. In total war, numbers win. The Luftwaffe's declining fortunes. By late 1944, the consequences of the performance and production gap become undeniable. The Luftwaffe bleeds experienced pilots at an unsustainable rate. Replacement pilots receive abbreviated training, thrown into combat with minimal experience. They face American pilots flying superior aircraft, backed by endless reserves of fuel, ammunition, and replacement. Aircraft. German pilot Werner Hoffmann, flying FW-190s, later recalls the growing desperation. We knew their aircraft were better. We knew they had more of them. We knew they could replace their losses while we could not. But we had no choice but to keep flying, to keep fighting. Every mission felt like it might be the last. You'd see new pilots arrive, fresh from training school. Within a week, half of them would be dead. The Americans just kept coming, wave after wave. The fuel situation becomes critical. Germany's synthetic fuel plants come under sustained Allied attack. Aviation fuel supplies dwindle. Even when aircraft are available, there's not enough fuel to fly them. Training flights are curtailed, leaving replacement pilots even less prepared. Operational units reduce sortie rates, ceding air superiority to the Allies by default. The P-47's, meanwhile, evolve beyond pure air superiority fighters. Loaded with bombs and rockets, they become devastating ground attack aircraft. The same robust engine and sturdy airframe that make the P-47 an excellent fighter make it ideal for low-altitude attack missions. Thunderbolts strafe German columns, destroy locomotives, crater runways, and generally wreak havoc on German ground forces. German soldiers learn to fear the distinctive sound of the R-2800 engine. That deep, powerful roar announces incoming P-47's, and there's little they can do about it. Anti-aircraft fire can damage the Thunderbolts, but the aircraft can absorb tremendous punishment and keep flying. Stories circulate of P-47's returning to base with hundreds of bullet holes, missing pieces of wing, damaged engines still running. The aircraft's toughness becomes legendary. The post-war reckoning. After Germany's surrender in May 1945, Allied intelligence teams examine captured German documents, including the R-2800 analysis from Rechlin. They find Schlemp's detailed reports, the metallurgical studies, the performance evaluations. The documents reveal how thoroughly German engineers understood their predicament and how powerless they were to change it. Schlemp himself survives the war and is interviewed by American technical intelligence officers. He's candid about his conclusions from 1943. We knew by then that we could not win, not through any lack of courage or skill, but simply because the industrial and technological balance had tipped decisively against us. The R-2800 engine proved this. It wasn't just a good engine, it was proof of an industrial system we couldn't match. He's asked if better German strategic decisions could have changed the outcome. He considers the question carefully. Perhaps if we had recognized our limitations earlier, we might have made different choices. But by 1943, the trajectory was set. We were fighting America's industrial capacity as much as American military forces, and that was a fight we could never win. Other German engineers expressed similar views. The technical analyses and reports from 1943-1944 show clear-eyed assessment of Germany's declining position. These weren't propaganda documents. They were internal technical reports. The engineers documented their findings honestly, even when those findings were unwelcome. American engineers, reading these documents after the war, gained new appreciation for what they accomplished. The R-2800 wasn't just a successful engine. It was a weapon of industrial warfare, demonstrating American manufacturing capability and technological sophistication. More than 125,000 R-2800 engines would be produced by war's end, powering not just P-47's, but also F-6F Hellcats, F-4U Corsairs, A-26 Invaders, B-26 Marauders, and numerous other aircraft types. The engine would continue in production long after the war, powering civilian aircraft and serving with military forces around the world. Some R-2800 engines remained in active service into the 1980s, a testament to the soundness of the design and the quality of the EU. Engineering. Few piston aircraft engines can claim such longevity. The broader context. The story of the R-2800 analysis is really a microcosm of the larger war. Germany entered the conflict with technological advantages in several areas and a well-earned reputation for engineering excellence. But Germany underestimated the importance of industrial capacity and the speed with which the Allies, particularly America, could mobilize resources. American industrial mobilization during World War II remains one of history's most remarkable achievements. In 1940, America's military was small and poorly equipped. By 1944, American factories were producing more war material than all other combatants combined. This wasn't just a matter of having more factories. It required developing new manufacturing techniques, training millions of workers, solving unprecedented logistical challenges, and maintaining quality while achieving massive scale. The R-2800 exemplifies this achievement. It was a technically sophisticated product, more complex than most automobile engines of the era, yet it was mass-produced with precision and reliability. Each engine required thousands of individual parts, many of them made to tight tolerances from exotic materials. Coordinating the supply chains, the subcontractors, the quality control, and the final assembly required organizational sophistication, matching the technical sophistication of the engine itself. German engineers, examining the R-2800, saw all of this. They understood they weren't just looking at an engine. They were looking at the physical embodiment of American industrial might. And they understood that Germany, for all its engineering prowess, could not compete with that might. The human cost behind the technical analysis and strategic implications lie human stories. German pilots who flew against P-47's, many of them young men barely out of their teens. American pilots who flew the Thunderbolts, equally young, equally vulnerable to the violence of aerial combat. Engineers on both sides, working to give their forces every advantage. Factory workers producing engines and aircraft, often under difficult conditions. The air war over Europe was brutal. More than 80,000 Allied airmen died in the bombing campaign against Germany. Luftwaffe losses were equally severe, with experienced pilots irreplaceable. Civilians on the ground suffered terribly from both deliberate and incidental bombing. The human cost of the conflict dwarfs any discussion of technical achievements. Yet the technical dimension mattered. Better engines meant better aircraft performance. Better performance meant more pilots survived combat. Industrial capacity meant more replacement aircraft and pilots. The war was won by soldiers and airmen, but it was also won by engineers, factory workers, and industrial systems that could produce the tools of war in overwhelming quantity and quality. The German engineers who analyzed the R-2800 understood all this. They knew their findings had life or death implications for German pilots. They knew that every P-47 escorting bombers meant more German cities destroyed. They documented their conclusions with professional detachment, but they weren't immune to the implications. Legacy and lessons. The R-2800 story offers lessons that extend beyond World War II aviation. It demonstrates that technological leadership requires more than invention or theoretical knowledge. It requires the industrial capacity to implement technology at scale, the manufacturing skill to maintain quality in mass production, and the resource base to sustain production over time. Germany had excellent engineers and produced innovative designs, but excellence in small batches doesn't win industrial wars. America's advantage wasn't that individual American engineers were smarter or more creative than their German counterparts. The advantage was systemic, an industrial base with vast resources, a manufacturing culture that valued process control and standardization, and the organizational capacity to coordinate complex production networks. These lessons remained relevant throughout the Cold War and into the present. The ability to produce sophisticated technology reliably and at scale continues to be a decisive advantage. Modern examples abound in industries from semiconductors to aerospace, to advanced manufacturing. The fundamentals haven't changed. Precision, quality control, process, optimization, resource security, and organizational excellence matter at least as much as pure innovation. The P-47 and its R-2800 engine also demonstrate the importance of engineering for operational requirements, rather than abstract performance metrics. The Thunderbolt wasn't the fastest fighter or the most maneuverable, but it was tough, reliable, maintainable, and effective across a wide range of missions. It was designed for the reality of combat operations, not for airshow demonstrations or theoretical optimality. German fighters often achieved superior performance in specific metrics, but at the cost of complexity, maintenance requirements, or narrow operational envelopes. American designers accepted performance compromises in exchange for operational flexibility and reliability. In the crucible of sustained combat operations, the American approach proved superior. The final assessment. When German engineers completed their analysis of the captured P-47 and its R-2800 engine in 1943, their conclusions were stark, but honest. They had examined one of their enemy's weapon systems in detail and found it to be excellent in design and superior in manufacturing execution. They had calculated what would be required to match it and concluded the task was beyond Germany's industrial capacity within any relevant time frame. This wasn't defeatism or lack of confidence. It was professional assessment of technical reality. The engineers had done their job, analyze the threat, evaluate the response options, report the findings. That the findings were unwelcome didn't make them less accurate. The R-2800 analysis didn't change Germany's strategic situation. By mid-1943, the war's trajectory was largely set, but it did provide clear evidence of the technological and industrial gap that had opened. For anyone willing to see clearly, the captured P-47 demonstrated why Germany could not win an attritional war against Allied industrial power. The engineers who conducted that analysis were not wrong. By 1945, the Luftwaffe was effectively destroyed. Allied air superiority over Europe was total. P-47's, along with P-51's, P-38's, and British fighters, controlled the skies. German pilots who survived the war spoke of the hopelessness of facing endless waves of Allied aircraft, of knowing that every loss the Allies suffered would be quickly replaced while German losses were permanent. The R-2800 engine, mounted in that first captured P-47, had told the future to anyone perceptive enough to read its message. It spoke of American industrial might, of manufacturing excellence at scale, of a nation that could design sophisticated technology and produce it in overwhelming quantity without sacrificing quality. It was a message German engineers received clearly, but could do nothing to counter. In the decades after the war, the P-47 and R-2800 became legends of aviation history. The Thunderbolt is remembered as one of the war's great fighters, rugged and capable, feared by its enemies, and trusted by its pilots. The R-2800 is recognized as one of the finest piston aircraft engines ever built, a masterpiece of mechanical engineering that helped power the Allies to victory. But perhaps the most important legacy is what that first captured P-47 revealed to German engineers in 1943, that wars are won not just on battlefields, but in factories, design bureaus, and industrial systems. That technological sophistication, without industrial capacity, is insufficient. That mass production at high quality is itself a form of technological achievement. The day German engineers evaluated the P-47's 2,000 horsepower engine and realized they could not match it was the day the air war's outcome became mathematically certain. Everything that followed was merely the working out of that industrial technological arithmetic. The R-2800's 18 cylinders had told a story of American power that no amount of German engineering brilliance could revise.